Great. We'll go ahead and get started. Thank you all so much for coming today. We're so pleased to see you all here. And to get started, we also have Zoom for those who maybe needed to meet there. So I'm very excited today to introduce our speaker, Professor Zuankai Wang, who is here from Poly University in Hong Kong. And he is a professor there who also is the Associate Vice President of Research. And he also started the nature-inspired lab there, where he has worked for quite a long time on surfaces, surface features, droplets, and droplet dynamics, and different things between everything from heating of plates to cause Leidenfrost, to droplets forming at different contact angles. And their group is very much inspired by nature, so I hope you have, if you have a chance, you can check his website. They have lots of beautiful images there. He's also now the associate editor, the editor-in-chief, actually, of Droplet, the Droplet Journal. So if any of you are looking to publish in that area, I think it's a good time to mention that. It's a great journal, and they have some wonderful publications now in there, and so it's a very good avenue to have your work highlighted. Professor Wang also has worked, as I said, extensively in fluids as well as surfaces, and has many inventions and patents to his name. And in addition to that, he has also, I think very interestingly, broken world record. He holds the world records for the most slippery, I think, droplet surface, which is quite interesting. And as well as many other prizes that are really too long to list. So without any further ado, I think I'll turn the time over to Professor Wang, and let's greet our speaker. Thank you so much.
Okay, thank you. Can you guys hear me? Okay, thank you very much, Ted. It's my great pleasure to come to this very exciting place. I really enjoy the hospitality, the food, the discussion. I met the older friend, and also I met Professor Chen. We are working in City University of Hong Kong. In many things, I think this place is very special. It's the first time for me. Even I was a little bit physically tired, but mentally I was very exciting. I really enjoy everything. Today I would like to talk about something which is very, very small, but very, very usual, I think, for this place, that's droplet. I think this is the best place in the world to talk about the topic. The first thing is, I think, we here really house the best researcher in the world in this field. We have several professors in mechanical engineering actively work on the topic, and also I think this is really the place which really appreciate the importance and the beauty of droplet. Okay, so I think, as scientists, every one of us has a dream, right? We dream to publish a good paper, we dream to have good data every week, and we dream to win awards. We secure large grant, and we also want to launch company. We want to supervise students. And our dream look like the droplet on the lotus leaf, right? Very beautiful, elegant. But most of the time, we encounter difficulty. In reality, it's not as easy to get good paper, get good data. Even we submit paper to Nature, and the editor reject our paper immediately, right? Most of the time, we suffer from grant, even not very easy to get company to launch. So our dream also look at the droplet on the lotus leaf. If we read the droplet from a certain height, the droplet will get shattered. Our dream will be shattered by the reality. But between the dream and reality, I think the gap is really small. So today I would like to talk about both sides of a droplet. I want to discuss, how we can see the bigger world, from a small droplet. I will start with my talk by, express my special gratitude to the KAUST. The reason is we are launched the Journal of Droplet. Professor CG really given me very exciting, beautiful movie. And Ted served as editor, with very professional, very helpful, Dan, contribute a good paper. I think, also the readers give us inspiration. I really want to take this opportunity to thank everything you did. I really appreciate. So droplet is not only beautiful, not only dynamically beautiful, but I think more important, droplet is closely linked with the practical application, from energy harvesting to thermal cooling, right? Droplet is everywhere, right? So, but if we look at the droplet, one very important part is, how the droplet interact with surface. There's many challenges there. So it's not easy, to control or design the surface, right? And so today, we'll start from nature's inspiration, right? Over the past 3 years, people complain the life, how tough life, because we can't travel. But if you look at a plant, plant permanently are trapped in a certain place. But still, plant doesn't complain, right? So plant get water from the root to top of the surface by capillary effect. The plant can keep self-cleaning, and the plant can harvest the water from the air. And also plant can keep, can even translate the kinetic energy, translate the water energy to kinetic energy to send the seed to the deep ground. And also, they can also get energy from the environment. So the approach we used is to borrow or learn the mechanism from nature. And then we try to translate this kind of fundamental understanding or even go beyond nature. Right? So nature is beautiful, and nature is highly adaptive, nature is highly intelligent, but more importantly, there's no waste in nature, right? So, there's no carbon emission probably in nature, and also nature didn't apply for any patent. We can learn from nature anywhere and anytime. So our concept is we try to construct material and then extend application to everything. We try to broaden the concept of Internet of Things to surface of a thing, right? So in the first step, we want to construct the surface. So Professor Tai just mentioned our world record. So several people probably heard our pancake bouncing work before, but today I will try to approach this problem from a new theory, or probably not good to call theory, but probably some concept I will mention is length scale matching theory. For hydrophobic surface, we want the droplet to shade away from the surface as soon as possible, right? So if we use a simple parameter, the contact time, we prefer to have very short contact time, right? But based on classical theory, the contact time is a constant, right? So if we look at here, when the drop contact the surface, the drop will spread, retract, and then jump away. The time is constant. Usually people focus on micro nanostructure because when the structure becomes smaller, the breakthrough pressure will become larger. But unfortunately, regardless of this kind of structure, the time is constant. In our lab, we approach this problem from opposite angle, right? So because we realize that the water also have a critical, very important length scale, that is length, capillary length. The capillary length about 2 millimeters. If we look at the feature size of a solid, usually people use micro nanostructure, but as I mentioned, the capillary length of water is 2 millimeters. So there's a huge gap between the micro nanostructure and millimeter scale. So in our lab, we try to shrink the gap. Okay, so what we did is by shrink the gap, we can strengthen the interaction between the solid and the liquid. Okay, now let's look. Oh. Okay, so let's look how we did that. As I mentioned previously, people just use micro nanostructure, but here, to enhance the interaction between solid and liquid, we increase the gap between the pillar. So the gap here is sub-millimeter. The reason is we want to have a stronger interaction between solid and liquid. This step is not good enough. And then to make the droplet come back easily, we create a vertical gradient. You look at the feature is pyramid. By control this kind of vertical gradient, on our surface, once the droplet contact the surface, the droplet will spread and then the droplet will jump without retraction. So here I want to mention this is solid liquid length scale matching. Without good matching, the droplet will leave the surface following the classical law. So by this way, we reduce the count time by 80%. Very similar to bird, right? In Beijing Olympic game, bird can run 100 meters about 9.59 seconds, but we can finish 100 meters within 2 seconds. Basically, we significantly reduce the contact time. So why we want to reduce contact time? If we can reduce the time, surface will be more self-cleaning, and the surface we can prevent anti-icing, we can save energy, and we can prevent the corrosion, and I think everything, we can do everything. Okay, so as mentioned in nature physics, even the work is very simple, but the Professor Boot mentioned this work really opened a new direction in this field, and also we get the world record for this. So this phenomenon is not only limited to micro nanoscale and also work in the large scale, right? By use length scale matching. For example, if we have a millimeter scale pillar, the droplet or the pancake can be much larger, maybe 20 centimeter. We also have this kind of a pancake bouncing. Okay, so following up over the past several years, there's lots of work in this field, trying to mimic or reduce the count time. I will not discuss today. So I just want to briefly mention another work about liquid metal. The reason liquid metal now become very hard because liquid metal has very large surface tension. But unfortunately, despite large surface tension, liquid metal is very sticky on solid surface because liquid metal can be easily covered by very thin oxide layer. Therefore, the liquid metal is very sticky. We found that very thin layer of water can prevent the contact between liquid metal and the solid surface, and thereby, the liquid metal droplet can bounce very easily. And also we develop model and to explain, why we have this phenomenon. And more interestingly, the larger the thickness of the water layer, the bouncing performance is larger. Okay, so I mentioned, how to control the liquid or liquid metal bouncing on the hydrophobic surface in the opposite direction. We want the liquid to flow spontaneously in one way and also flow in the long range. We know we can't run marathon at a very high speed, right? We can run 100 meters at a high speed, but we can't run long distance. It's possible to run marathon at high speed. The answer is yes, right? So the method we used, we learn from nature. In nature, that the beetle is locally the surface hydrophilic, but globally the surface water repellent or superhydrophobic. It's because the beetle is covered by reentrant structure. There, the reentrant structure. The reentrant structure modifies the energy barrier. So even the surface is hydrophilic, but globally it's superhydrophobic. So conventionally, on hydrophilic surface, the liquid will spread symmetrically, and it's hard to control the spreading. So in our lab, we want to achieve directional and spontaneous liquid flow. So the secret is we borrow or we learn and use the reentrant structure here by this way, and by this way, we can achieve the directional liquid flow at here. The liquid flow only in one way and at very fast speed. But one very interesting point here, when we use this reentrant structure, as I mentioned earlier, the surface will repel water. But the question now, why on our surface the water will spread rather than build up, right? As published in Science in MRT and in Science in 2014 UCLA, the both science paper talk about how to make the surface super hydrophobic use reentrant structure. We also use reentrant structure here, but why on our surface the water spread, water flow? Because the secret is here. In our design, the spacing between the reentrant, is millimeter scale. So as I mentioned earlier, if the scale matching the capillary length, right? So the liquid, we modify the energy barrier. So this is the reason, why the liquid can flow spontaneously and directionally and also long range. Okay, not only this kind of behavior, if we engineer the pattern, the liquid can flow, following our design. This kind of design is very useful for thermal cooling, right? Especially for vapor chamber. For example, now Huawei, Apple, right? They use the vapor chamber to cool down our cell phone. They want to have very thin vapor layer. Usually for vapor chamber, they have two sections. Very important, the two components. Here they have boiling, and here they have condensation region, right? So the liquid should flow back from the condensation area, to the boiling area. So by using our design, we can make this kind of flow much more efficiently. Okay, so not only we have two-dimensional liquid diode, I call the liquid diode, but we can also achieve three-dimensional, collaborating with Professor Yu in City University Hong Kong, we create three-dimensional liquid diode for flexible electronics, right? So currently, one challenge for flexible electronics is the sweat, right? When the skin will sweat, the sweat will permit the contact between electronic device and our skin. Right, and then make the detection, make the signal weaker and weaker. So by using this kind of 3D liquid diode, we can repel the sweat from our skin to our side much more efficiently. Okay, so I mentioned, how to make 2D and 3D dimensional. Another one also we learn from nature, especially from the tree we call monkey puzzle, and then we mimic the two structure here. The tree is covered by reentrant structure, and then we found that the liquid, will flow spontaneously, and also we didn't apply any pressure and flow at a very high speed. The secret is the same as I mentioned earlier. Even the surface covered by reentrant structure, suppose this kind of structure will give rise to water repellency. But on our surface, liquid flow, the reason is if we look at the spacing between the reentrant is millimeter scale. So this scale is comparable to capillary length. So this is the reason why, by matching, the length scale, we can observe some unusual phenomena. Okay, so not only by control the wettability and also structure, over the past 2 or 3 years in our lab, we also adopted to surface charge. And by controlling surface charge, right, we can make that droplet climb the wall, the droplet can follow our action, right? So even we can also control the droplet transport by friction. For example, by contact electrification, the droplet will follow our motion. This one is much more powerful, than the electrolytic. For electrolytic, you have to apply voltage, right? It's quite difficult to achieve. But for our technique, just by control the friction, right? And then droplet will follow the motion. It's a very, very simple but very powerful technique. Okay, so the length scale matching is not only limited to droplet, but also applicable to solid particle. So for liquid droplet, it's very easy to get jumped because when two droplets merge, the surface energy will be converted to kinetic energy. So this is the reason why the droplet can jump at a high speed. But for solid particle, it's different. Solid particles are rigid. There's no coalescence between solid particle. And at a small scale, the adhesion force is dominant. So there's no way to repel the solid particle. So this is the reason why we have PM 2.5 problem. But nature is very, very smart. I will show you an example, the honeybee, right? The honeybee shuttle between the different flowers. But if you look at the antenna of the honeybee, always keep self-cleaning. So my students are very puzzled by the honeybee. And then we look at the honeybee again here. The honeybee developed a comb. You know, look here, the comb. I don't know why this one looks like doesn't work. Yeah, here if you look at the comb, actually the comb in terms of the shape, the comb is exactly the same as the comb we use every morning. But there's two differences. The first one is the size. The length of each pillar around 30 micron. It's very, very tiny, right? So the artificial comb we use in the morning usually is maybe 2 centimeters long. And also, you know, if we measure the stiffness, you know, we can see a gradient in the stiffness. The tip is very soft. The bottom is very rigid. So we have a stiffness gradient along the pillar, you know, because this kind of gradient, when particle interact with the pillar, you know, the particle can be shed away much easily. Okay, it works. Okay. Oh, probably we have to use the USB. It will help. Oh no. Okay. Okay, that's fine. So the pillar, if you look at the diameter of a pillar, it's comparable to the particle. Okay, so the size is comparable. You know, this kind of interaction gives rise large acceleration. You know, this kind of acceleration can be large to 3,000 gravity. You know, this is the reason why the particle can be shed away very easily, and then, you know, the honeybee can keep self-cleaning. So based on this kind of inspiration, you know, in our lab, we developed robot to clean the solar panel. You know, one problem for solar panel is, you know, after 1 or 2 months, the surface will be covered by the particle, and then, you know, the energy efficiency will become dropped, right? So by using our robot, you know, we can make the solar panel work much more efficiently. Okay, so our theory is not only limited to single phase, but also applicable to multiple phase, especially in thermal heat transfer, right? In condensation and boiling, we not only have a droplet, we also have the bubble. And if you look at the bubble or droplet size, it's very, very small. In this case, the size is, you know, usually several micron. It's much, much smaller than the capillary length. At this size, you know, adhesion and even the lightation become very important. It's not that easy to make the bubble and droplet to leave the surface easily. To make this kind of droplet to leave the surface easily, you know, we come up with some a special design. For example, if you look at our design, the left part is flat, the right part is curved, right? You know, and here we have the asymmetric tip. The tip is very small. The tip size is comparable to the droplet size, okay? So if you look at the second part here, there's two unusual phenomena. The first one, you know, we have a large droplet on the flat side, and we have a small droplet on the curved side. And you can see clearly the large droplet will move from left to right. That's unusual. Now, usually, the big droplet will eat the small droplet, right? The small droplet will be captured by large droplet. But in our case, the large droplet will flow to a small droplet. Another one is the right side is curved, the left side is flat, and the droplet will move from flat side to curved side. This is also unusual. This kind of unusual finding are caused by this spatial curvature. Because this kind of spatial curvature, especially the size of the droplet is very comparable to the chip size. The energy barrier is modified. We have a simple model to explain why we observe this kind of phenomena. If we continue to move forward, if we have this kind of pillar array, especially we created the gradient, right? And then the droplet will fly in the air. By this way, we can achieve long distance and fast transport of a small droplet. Okay, so in thermal cooling, we evolve phase change, right? For phase change, at the beginning, we want to have fast nucleation. Of course, according to the energy analysis, we prefer hydrophilic surface, but on the other hand, the surface should be hydrophobic, otherwise the surface will be covered by the water layer. So there's a contrast, right? Complicated, right? One side is hydrophilic, another side is hydrophobic. To resolve the problem, we created this kind of pattern, on the wall is hydrophilic, favorable for nucleation, and globally superhydrophobic is for droplet departure. By this way, we can decoupling the contrast in hydrophilic and hydrophobic property, and then we can achieve excellent heat transfer performance. So I briefly mentioned how we use length scale matching to solve two important problems. The first one, on hydrophobic surface, we have a world record. On the hydrophilic surface, we can achieve liquid diode transport. Now I want to talk about application, because the application is really important to address our emerging crisis. The first application, I want to take advantage of the latent heat of the liquid. So today, if we look at our current technology, we have a ChatGPT, we have AI, we have the open AI server, right? Every people are excited by this kind of emerging technology, but probably most of the people didn't realize, underlying the technology, we need cooling, right? To cool down our cell phone, to cool down our data center. Without cooling, this kind of device, will not work, right? When people use the ChatGPT day and day, we create lots of thermal problem, right? But for thermal, one technique to address thermal is just use latent heat. Probably we know, right? So latent heat, by using latent heat, we have the greatest technology advance in our history. Watt updated the steam engine, right? Watt is not the first one to invent the steam engine, but Watt is very smart. Watt learned the concept of latent heat. Watt separate the condensation from boiling, and then he updated the design. Finally, we created the greatest technology advance in history. And later on, we have the air conditioner by using latent heat, right? In here, even the weather very hot, people can enjoy life, right? So today, in the information technology, right, we want to also use the latent heat of the liquid to cool down our chips. When we put more and more transistor in our computer chips, we have more and more heat flux, right? Unfortunately, with the coming of AI, right, the problem is even more severe than what Moore predicted, right? At that time, the integration intensity will double every 1.5 years. But now, every 2 or 3 months, the heat flux is doubled, right? So if you look at data center globally, there's huge market. The trend become even more obvious because more and more people use AI. So how we can cool down, data center, how to cool down our EV car, how to cool down computer chips, right? Previously people, just use air cooling, but the air cooling is not efficient. AI has come, but the technology to control, the technology for cooling, we still stay in the same technologies we used before, right? For example, Huawei launched the new cell phone, the plate. It's just for sure. People can visualize, how they use microchannel to cool down the computer. They sold 40 million just within 1 week. This is not new technology. It's just Huawei is very smart to just demo, to allow people to see the transport of the liquid, right? It's a huge market, right? And in some company, they integrate the electronics device with the fluid device together, right, to make the cooling. So despite progress, we still suffer from several challenges. For example, the cooling, the energy consumption is huge, the water consumption is huge, and also the CO2 emission is huge. Can we develop a blue technology that is resilient, sustainable, scalable, right? That is our dream. So in our lab, over the past 15 years, we adopted to surface engineering, okay, to tackle this problem. By control the surface pattern or surface wettability, we modify the nucleation, and departure behavior of droplet bubble. As a result, we want to enhance the transfer. So this is what I mentioned earlier. By decoupling hydrophobic and hydrophilic property, we can enhance the droplet condensation. So today, I want to talk about another part of condensation is boiling. Let's do a very simple experiment together, right? When we increase temperature of the plate, we can see the droplet become evaporated. If we use a very simple parameter, the evaporation time, we can see with the increase of temperature, the time will become shorter and shorter. I think this is very, very normal. It's very simple to explain. But something unusual happens if we increase temperature above 250 degrees. You can see the droplet will bounce on the plate. There's no evaporation. So the evaporation time becomes much, much longer, probably up to several minutes. So what happened here? The phenomena here actually is not new. The phenomena was explained by Frost back to 1756. Actually very simple. At high temperature, the water will evaporate. As a result, between the liquid and hard surface, we have a vapor layer. The vapor layer will block transfer between liquid and solid. Suppose, right, the liquid has very large latent heat. We want to use latent heat to cool down the hard surface. But unfortunately, the formation of vapor layer make the heat transfer a disaster. Okay, so the phenomena will become more apparent if we have two droplets. Each droplet will be levitated by the vapor layer, and between the two droplets, you can see in the vapor layer very clearly. This is triple Frost effect. Okay, so Frost effect is the origin of surface, interfacial phenomena back to 1756. Right? The phenomena actually is quite ubiquitous, not only liquid, but also solid. For example, the dry ice also have this phenomena, right? Or even the soft matter also have this phenomena. Okay, and not only occur on solid surface, the phenomena also occur on liquid surface. That one is the Frost appear on the liquid surface. If we look at theoretically, the problem is very simple. On the hard surface, we have the vapor layer. Suppose, right, the droplet, the vapor layer is symmetric. Suppose the droplet should be very still, but in reality, the droplet is very mobile and just depart from a surface very easily. The problem is the droplet usually surface is tilted, right? So the droplet behave like a wheel, right? My collaborator David Curry published a paper in Nature Physics. The droplet just depart like a wheel. And by control the surface pattern, for example, subatrophobic or subatrophilic pattern, or by control the geometry of the surface, we can rectify the vapor layer, right? So people used to reclayer the liquid, but here we reclayer the vapor flow, and then the droplet will flow in one way. That's very cute, right? So if we move one step further, right, we can leverage on this kind of motion to produce power, but unfortunately, the energy efficiency is quite low. Okay, and the good side of the Latin frost effect is we can reduce the drag. I think Professor C.G. published lots of paper in PIL, right? Use Latin frost to reduce the drag, right? At the beginning, right, we have a liquid-solid friction, but now by using the vapor layer, we reduce the friction. In our lab, we use Latin frost to promote mixing, right? Especially to promote mixing of a highly viscous liquid, right? For highly viscous liquid, the mixing is almost impossible. By using Latin frost effect, the droplet can spin at a very high speed, and then we can enhance the mixing efficiency, right? So there's some magic part of a Latin frost, right? You can cleave the molten steel with a bare hand. There's no damage to your skin, right? But you should do very, very quickly, and because of Latin frost effect, right? And also in KAUST. Here, reported in Nature, I think also by Professor C.G., right? But make the surface super hydrophobic, we can make the Latin frost more stable. Basically, the vapor layer can become more stable, right? But the most important, I think, or probably dangerous, is for heat transfer. On one hand, when we increase temperature, we want to have a bubble formation. That's good, because latent the heat, we can absorb the heat, right? That's good. But if we increase temperature further and further, we have a continuous vapor layer, as shown here. We reach CHF, we call critical heat flux. And if we continue increase temperature, the vapor layer will block transfer between liquid and solid, and then we have a problem. If we couldn't dissipate the heat from the surface, when the surface temperature above the melting temperature of the material will be melted. So this is the reason why in Japan, back to 10 years ago, we have the Fukushima nuclear power plant. It cost $300 billion loss. And also this is the reason why we just use gas cooling rather than liquid cooling for engine, right? Because usually for engine, they work at more than almost 2000 K, right? At that high temperature, we have Latin frost effect. The liquid cooling, it doesn't work. People just use the gas cooling, but we know the gas cooling is not efficient. So if you look at the history over the past 2 centuries, people really want to develop a technique to significantly increase Latin frost temperature. If we can increase Latin frost temperature above the melting temperature of the material, we can fundamentally prevent occurrence of Latin frost effect, right? If by doing so, we can make our EV car, there's no disaster, there are no accident, we can create new engine, right? We can avoid nuclear power plant in Japan, also in the world, right? So the question is, how can we make it, right? We learn from ChatGPT. ChatGPT is actually very, very humble, right? He mentioned while it may not be possible to completely eliminate the Latin frost effect, it's true. It's almost impossible to fundamentally, completely to prevent Latin frost. But still, ChatGPT gives us some hints. For example, make the surface rough, make the surface control the wettability, applying some external force. But despite this, It's not that easy. So back to several years ago in our lab in CTU, when I worked at the CTU, at that time, we don't have a good idea to fundamentally prevent Latin frost effect. But we changed the concept. Okay, if we can't prevent Latin frost effect, how, once the surface have Latin frost effect, can we shift the droplet from the Latin frost region to the boiling region, right? For example, we can't compete with you on this domain. How about, we shift from another domain, right? So we have Latin frost here, but once we have Latin frost effect here, the droplet will be shifted from here to the boiling region. Boiling region is we want, because in boiling region, we have very good heat transfer performance. But the idea is we just create the pattern because at different pattern area, we have different critical Latin frost temperature points. By doing so, we shift the droplet from Latin frost region to the boiling region. Here, I want to point out a very, very exciting work published in Langmuir back to 2017. So in this work, the author used a membrane. The membrane is somewhat conductive. I think it is normal, right? Because we want a permanent heat transfer. And the membrane has nanoscale pores. And then the Latin frost temperature about 600 degrees. There's some good part of the design. Also, there's some weakness. The weakness is the membrane have nanopores. The liquid will not spread easily on the surface. Actually, we want the liquid spread spontaneously, just like a sponge, right? But here on this membrane, the liquid seldom spread, and that's not good. And also, the membrane is conductive. Okay, so later on, we have a new design. So before I talk about our new design, let's revisit the problem again. So on one hand, we want to control the nucleation. We want to have the nucleation bubble smaller and smaller, faster and faster, right? Once the bubble is nucleated, we want the bubble to depart from the surface quickly, right? And then we want liquid flow back. If without flow back, without a weak structure, without the capillary effect, the surface will become dry. So we can not only control the bubble, also we should control the liquid flow. So in our mind, probably we have the first image. The first picture is the surface should be super spreading. Once the liquid contacts the surface, the liquid should spread as soon as possible, right? If the liquid can spread as soon as possible, we have very thin layer evaporation. We know that thin film evaporation is very effective for heat transfer, right? The problem for Langmuir design, the liquid will not spread very, very well. Okay, so can we strengthen the liquid spreading? The second one, can we make the surface temperature profile not uniform? The reason why we have a Latin frost effect is because we have a uniform vapor layer. If we have non-uniform temperature profile, probably we can shatter the vapor layer. For example, at the beginning, we have uniform vapor layer. If you have uniform vapor layer, we can shatter the vapor layer into different patches, into different domains. Or fundamentally, we can prevent the formation of uniform vapor layer. Probably, if we can create non-uniform temperature profile, we can prevent the formation of uniform vapor layer. The third one, also very important, as I mentioned, we should not only control the liquid flow, and also we should control the vapor flow. In Hong Kong, right, we very, very small place is different from here, right? People, we turn to MTR, we turn to subway to solve the traffic. The reason is, when the people get together, we have a traffic problem, right? By use MTR or bridge, right, we decouple the flow of the people from the car. For example, if we decouple the flow of water from the vapor, vapor and water, they will not fight. they will work together to make a great, all right, together, right? So with this kind of image in our, this kind of thinking in our image, and finally we come up with this kind of design. The first one, right, we want to have super spreading, and we use porous material. And also, as I mentioned earlier, we want to make length scale matching, for example, pancake bouncing or liquid diode. If you look at spacing our pillar, basically the pillar here is thermoconductive. We want to use pillar to enhance heat transfer. But the space in the pillar is roughly millimeter scale. We want to enhance the interaction between liquid and our solid surface with length scale matching. And also the membrane very porous, very similar to sponge. You know, we want the water become absorbed immediately. And then to decouple the water flow from vapor, we create a vapor channel here. Once we have vapor, the vapor will flow this way, the liquid will flow along the membrane. So we decouple the flow between water and vapor. So this is our design. Let's see what happens. And then you can see here, without the design, above 300 degrees, we have lattice frost effect. But even here, is above 1,000 degrees, we still see super wettability, super spreading. And then, you know, after super spreading, the liquid will evaporate and cool down a hard surface. As long as we have water flow and we can maintain a cool state. So here in our paper, we report the temperature 1,100 degrees, but actually the temperature can be much higher because we can only apply up to 1,100 degrees. So basically, there's no limit to this phenomenon. Okay, so now I think very important about the key parameter, right? This is our rough design, but we have to control the parameter. You know, on one hand, right? So here we involve the competition between conduction and convection. If we focus the membrane, the membrane really have two options. On one hand, the membrane can be heated up by the pillar. On the other hand, the membrane can be cooled down by the water. Which one we favor? We favor the membrane will be cooled down by the water, right? If the membrane will not cool down, or if membrane will be heated up by pillar, you know, we can reach a uniform temperature. That's not what we want. Okay, so by doing so, you know, we check the competition between conduction and convection. You know, we get, you know, the thermal conductivity, right? We should control that. On another one, we should control the decoupling between the water layer and the vapor layer. So basically, we want to stably trap the vapor between the membrane, inside the membrane. Okay, so by this way, you know, the vapor, you know, can flow upward, not, the vapor will flow downward rather than upward. If the vapor flow upward, because the water will come down from top, right? If the vapor flow top, they will fight, right? So the vapor now, you know, by calculating the vapor pressure and the working capillary pressure, you know, we can control the porosity of the material. Okay. In terms of manufacturing, it's very simple, it's scalable. You know, we can fabricate this kind of structure or any kind of material. If it's not easy to fabricate, we just, you know, make the very thin layer and then deposit on the material. Okay. So I think, you know, scientifically, I think to some extent, you know, this work probably helped to answer the very, very fundamental question. You know, what are the limits of heat transfer in matter? But I think this is for phase change heat transfer. Chemistry point of view, you know, superweighting is top 10 technology in 2021. But conventionally, the superweighting only occur in a very narrow temperature range. But for the first time, we obtained superweighting to a temperature above 1,000 degrees. I think the application is very broad, right? So range from EV car cooling, data center cooling, weapon, nuclear power plant, right? And even in our lab now, we use this method to cool down, for cool down stem cell, organ. Because this phenomena, even for nitrogen, they have no lateral force effect. Okay, so U.S. and Europe approach us, right? So use our technology to make better design, for thermonuclear fusion facility or power plant. So here I want to mention a very, I think a very funny story here. I mentioned the phenomena was explained by Frost in 1756. But actually, the phenomena was first discovered by Hermann in 1732. Probably most people never heard Hermann before, but Hermann is the father of physiology. He is the first one to introduce temperature measurement to clinical hospital. Now we know when we go to the hospital, the first thing we do is measure temperature, right? So Hermann is very, very famous across Europe. And very coincidentally, Hermann grew up in a city called Leiden. And he graduated and also worked in Leiden University. And Frost, in his last name, also have Leiden. Very similar to in China, we call Wang Li. We share something very, here share the Leiden. One is the affiliation, another is name. But the story will become more interesting if we look at an academic family tree. So I graduated from RPI, the Rensselaer Polytechnic Institute, in 2008. And if you look at family tree, it turned out Hermann is my advisor. I was his 14th generation student. It's very so coincident. So Hermann is the first one that discovered the phenomena. To some point, to some extent, I help to address or resolve this historical challenge. So, and also many people know when I studied for my PhD, Professor Nicholas Clark is my third PhD advisor. So today I finally realized, at that time I complained my life is terrible. Now I realize, the reason why I have a third PhD advisor because I want to be a student of Hermann. Okay, very coincident. Okay, so this phenomenon not only occur for droplet and also for pool boiling. Now we use this design in our lab to improve the performance of pool boiling, and then we move to the flue boiling, the microchannel, and also we combine with reduced cooling. Work with collaborating with a professor in City University, Hong Kong. We use ceramics, to achieve good release cooling. This kind of design is mechanically robust and also can be used in the top of a building to reduce energy. And quickly I will discuss in our lab, there's another direction is we want to leverage the power of a droplet. That's why we want to translate the kinetic energy to electricity. So, people know the Kelvin water dropper invented in 2 centuries ago, but, the efficiency is very low. But we made a difference back to 2020 in our lab. We use very simple design. One droplet can produce 140 volt voltage and light up 100 LED. Right? So that design is very simple as shown here. So basically, we increase energy efficiency by 1,000 times. That is for liquid-solid interaction. And later on, we extend to solid, liquid to liquid, solid to gas. As long as people use our design, we keep the record, for every efficiency. So basically, the concept is very generic and very powerful. So today, for example, if the water droplet hit the plant, we produce power. The droplet hit the solar panel, we get power. In the sunny day, we had power, and in rainy day, we have the raindrop. We have power. We will walk. We can collect energy. Today, for one single droplet, this is real-time video. We can produce 8,000 volts, and we can light up 20-watt light bulb. But the problem is this is just a peak, not DC. But still, people can really appreciate the power of a single droplet. Not only droplet, even bubble, one bubble, right? It's only 20 micron size. We can light up 40 LED. We can, this is very important for offline. For example, in the sea, ocean, there's no electricity, there's no grid. We can just have this energy from a bubble. Finally, I want to show you another funny design. The drinking bird. I'm not sure whether heard of a drinking bird before. The toy, right? It's just $10. You can maybe USD is $1. You can buy in the store. The drinking bird can drink the water, forever. Okay, so the reason why a drinking bird can drink the water forever, actually not that simple. Einstein studied this phenomenon for 3.5 months, and Einstein didn't succeed. Okay, the reason why the drinking bird can drink water forever, because at the beginning, I saw here, if we have water on the tip here, the water will evaporate, and here the beak will become cooler, right? And then we have condensation occur here. Inside of the tubing, we have a special liquid. The melting temperature about 40 degrees. Okay, the melting temperature is 40 degrees. So the top, once the temperature here is smaller, we have a lower pressure on the top, and we have high pressure on the bottom, and the liquid will flow from bottom to top. And then the gravity center will shift. So this reason, once we have a liquid at the beginning, the toy will always move backside and then drink the water forever. And then we use this technique to translate the latent heat of water. During the evaporation, we have latent heat, and then we have toilet to translate heat to kinetic energy, and then we use the TNG to get power. Okay, here we have the power, right? So the performance is much, much higher than our previous technology. So as long as when the drinking bird drink the water, we continuously produce energy. So a very, very efficient design and very cute. Okay, and then finally, at just 1 minute, and in our lab, we control the coating, make the coating durable, robust, repel the water, and also mechanically strong. Okay, finally, as mentioned by Ted, we have launched a new journal, Droplet. To me, the droplet in each word stands for a different meaning. So this, fortunately, we will have the first impact factor next year. And I think the droplet title is very small, but the title is very similar to cell, right? Cell is small, but cell is very broad. Not only published paper on cell itself, but also all the work across the life science, but also the same for droplet. We not only focus on droplet, we focus on everything as long as they have some element related with droplet bubble. So as I mentioned, the droplet already been selected for inclusion in Web of Science, and we will have the first impact factor next year. I think the first impact factor should be more than 10. And then Professor Daniel already published a good paper in droplet. I think, okay, and also, one more, sorry. We will have a conference, microflow and interfacial phenomena in Hong Kong on June 20 and 24. Hopefully if you are interested, you can let me know. We can meet in Hong Kong. Okay, I think finally, today I discussed one very simple theory, and then use this theory, you can answer two physical limits. I discussed three applications. The first one is thermal cooling to leverage on latent heat of liquid, and another one is some energy harvesting to leverage on the kinetic energy of the water. And then how to design robust coating. Thank you very much.
Thank you very much, Professor Wang. I think we have time for a few questions, but I know some people need to go, so feel free to go if you need to. We'll try and keep questions to under 5 minutes before the next class. Yes, in the back here. Yes, you can. I'll come to you. I'll come to you.
Thank you for the wonderful talk. I have one naive, I would say, question. I was wondering what kind of water you use for your experiments, for the droplets. And for example, if you would see differences in the droplet dynamics, if you use, for example, rainwater or water from the sea.
Okay, I think that we didn't control the water specifically. I think for most of our experiment here, we just use normal water, even the type of water, a raindrop. So basically, we are not affect our experiment too much. The reason is, we care about certification. The most important is certification. Okay, unless you have some surfactant or special component which can modify certification significantly, otherwise the phenomena will be similar. Unless for thermal for energy harvesting, so that's why we should care about the salt, the ion concentration slightly, because the electricity generation is relatively with the ion concentration. Okay, thank you.
Excellent. One more right here.
Fascinating presentation. Thank you so much. I'm curious to see the slide that you skipped through it. It had Tesla on it.
Oh, the Tesla?
Nicholas Tesla.
Yeah.
But we could not pass through it. I wonder if you could go back to it and just briefly explain the point.
Oh, you mean there's one slide about Tesla, right?
Yes.
Okay, yeah. So that one is, we want to achieve very good the cooling. Okay, so normally I think it's here, right?
Yes.
The Tesla.
Yes.
Okay, so basically in the microchannel, the flow is chaotic. The flow is because we have two phases. We have water, we have a bubble. So in order to achieve directional flow, because without good control, the pressure drop will be large. Okay, by use this kind of design, we can achieve directional flow. So by this way, we can enhance the thermal property. Yeah.
Very interesting. Thank you.
Hi, Professor.
One last one, yes.
I'm here.
Okay.
Regarding your invention on the Leidenfrost, this material, you said it can go up to 1,000, not to. Could you please, how durable is this? Like, you already testing in the real life applications, or is just laboratory pure testings?
Yeah, our temperature can go even beyond 1,000 degrees. That is based on our experiment. For example, here, we have we heat up the material. So here, right, we measure the temperature here is more than 1,000 degrees. But the temperature should be below the melting point of the material. Otherwise, the material will be melted. As long as the material, the temperature is below the melting point, we can prevent the occurrence of a Leidenfrost effect.
But what's the composition of the things which you are putting? Like how you made it?
You mean how we measure temperature, or how?
No, the one which on top of it.
On top?
Yes.
Yeah. On top is here. We control the temperature on the top. Because it is, the substrate is very good for heat transfer, and then we just we just release the water, right? And here we have on the top we have a thermocouple. We have a thermocouple to locally track or measure the response of temperature. Yeah, we have a thermocouple. Yeah.
Excellent. Well, thank you so much, Professor Wang. Thank you for coming, and we're really grateful you came. And if other people want to meet or talk to him, please let us know, okay? Thank you.
Thank you.